Hello everyone, today we're going to talk about binomial trees for American option pricing. The basic idea is that we build a tree with different possible stock prices. At each step the price can either go up or down. After constructing this tree we use backward induction to calculate the option value at each node until we reach the value today. Now as you can see there's a small difference compared to the BS model. That happens because the number of nodes in the tree is still relatively low, so the estimate is less precise. But as we keep increasing the number of steps in the tree, you can see the option value converging to the BS price, and the difference between the two prices keeps getting smaller. So after around 500 steps, the result basically converges. Now, everything we just discussed was considering a European option, but when we move to an American option, we also need to consider the early exercise premium. So basically, whenever the difference between the underlying price and the exercise price becomes larger than the calculated option value, it becomes optimal to exercise early. In those cases, we see an early exercise premium at those nodes, which are highlighted in yellow. And because of that possibility of early exercise, the American option ends up being more valuable than the equivalent European option. Now, as you can see in the first graph, there's no value from early exercise when the dividend yield is equal to 0. So in that case, there's no difference between the price of a European call and an American call. This happens because exercising the call early would mean losing the remaining time value of the option without gaining anything in return. The difference only starts to appear when the dividend yield becomes higher than the risk-free rate. In that situation, the dividends that you miss by holding the option instead of the stock can actually outweigh the time value of waiting, making early exercise optimal in some nodes. But this logic doesn't apply to put options. Even when the dividend yield is 0, puts can still have an early exercise premium. That's because exercising early allows the investor to receive the strike price sooner and invest that cash at the risk-free rate. So unlike call options, American puts can be more valuable than European puts even without dividends.
So let's start coding. Well, the Cox-Rockström-Stein is also known as DCR binomial model, is a discrete time framework for pricing options. So instead of assuming stock prices move continuously, we break time into small steps. And each step, the stock price can either go up by a factor called U or go down by a factor called D. And how those factors are calculated? Well, we have the delta T, which is the length of each time step, and up and down, which depends on factors such as the delta T and the implied volatility, the same thing of the down factor, and a risk neutral probability that depends also on the risk-free, and the dividend yield, very similar to the geometric Brownian motion formula, the same variables. And basically, how we gonna model it? Well, it's basically a matrix with the stock price that start in a value and go ups and down according to a certain standard deviations. And this matrix is basically calculated by using loops. And well, firstly we calculate all the stock prices in this array, and in the end we do something called backward induction, which is in the last step of the tree, we calculate the option price, and the option price of the other nodes we calculate as a discounted way until we get in the first node, which will be the option price. Well, and so let's start here with the code. I'm going to import all the relevant libraries and start with something called the modular approach. What is this? I'm gonna start creating small formulas, small functions, and then I'm gonna put all these formulas into a big one. So let's start defining the first parameters, which are exactly these ones here. So I basically put all these parameters to the formula, and it's very important to understand what is this dt. So basically this example, this is an option that expires in 1 year, so t equal 1 year. And to start, I'm using very few time steps. I'm using 4 time steps. So if I'm using 4 time steps, 1 divided by 4 is 0.25. So it's as if I was calculating the stock price in each quarter. And for example, if I would choose, I don't know, 1000 time steps, it would be, I don't know, every 30 minutes or every second. If I choose a very large n, would be as if it was like every milliseconds, as if
in real life because the stock price is always being precified every second or every millisecond with a high frequency trading. So I basically input all those formulas into this one called CR parameters. And there is this one here called a CR stock. And basically, what is this doing here? I'm basically creating an array of zeros. Call this function here smart. So I'm gonna give an example. This function basically what it's doing is creating an array of zeros with a number of rows equal the n plus one. So will be, since n I choose 4, it's gonna be 5 rows and 5 columns. And why this plus one? Because the first column should be the stock price, and it's gonna be increasing or decreasing in each node. So let's go back here to this first function. So here, as you can see, for example, the stock started in 100. If it goes up, it goes to 110. If it goes down, it goes to 90. And for 90, if it goes up again, it goes to 100. Or if when 110, it goes up again, it goes to 122. So basically, this is the array with all the different stock prices going up and down in each node of the tree. So let's get our inputs. I'm gonna put an add the money call. There's a reason why every event, every example, I use an add the money, because when you specify the money, I think would be a bit more realistic in the real life, because unfortunately, Black-Scholes and binomial models, they have a problem which they don't consider skill, and the skill is deeper when the option is all the money. So when the option is add the money, you kind of have less of this problem. This is why I think the most realistic example would be to use add the money options when I'm specifying with these methods. And well, here we go. And basically up, down, I put all in these parameters, and I get these factors based on the stock price. So yeah, it is 0.5, like 1 divided by 4, and up and down, and the risk neutral probability. So yeah, here's the tree that was made before. Well, before going to American options, let's try to replicate the Black-Scholes model by using binomial trees. Well, what I would like to explain here, that is basically, now that I have the stock prices, I'm gonna, in the last node of the tree, I'm gonna specify the option, which would be the stock price at that node minus k, or if it's negative, it's gonna be 0. And bring these basically to the present value according to the all nodes you have of the stock price. Well, so here we go. This is another function called the CR European, and here I have all the variables to create this array. And well, here we go. I first put if it's gonna be a call on our put, because well, it's gonna change a lot of factors depending on what you're gonna choose. Because when you use a call, it's gonna be like the last stock price minus k, and if it's a put, it's gonna be the k minus the last stock price. This is basically meaning that this is the last node of the tree. So well, the last node is gonna be the option price. And as soon as I get the option price, I'm gonna do the backward induction. So this is a loop, and basically what it's doing, I'm basically drawing the option price in each node of the stock price. So basically here I have the OMAT, I put in this function here, and I get the European stock price. How do I do this? It's because I got the first row and first column of the matrix, which is basically the European call price, like this one here, 8.76. And here you can see all the difference value. I bringing all this to present value. So according to the risk risk neutral probability. And well, this is the final matrix of the European option price. And now I'm gonna compare these values with the Black-Scholes benchmark. I have a video explaining how the Black-Scholes is built,
And I'm not gonna go in details about it. I'm just gonna use this to compare with those variables. And well, this is like the Black and Scholes price, and this is the CRR price, which again is the first row, first column of the matrix. And I'm gonna calculate the difference. And this reasonable big is the CRR option is like 0.46 lower than it. Like why? Because the n is low. Let's change the n so you can see the difference. Like so I basically changed the value of n to 200, and now we're gonna see here the difference. You see, decrease to minus one, like almost zero. So from 0.4 reduced to almost like zero. And now the most important part of the video, which is how to specify American option pricing and the reason why people still use binomial trees. And what is the difference? Well, American option price, you can exercise at any value, not necessarily at the expiration date. And how do you account for this difference in the nodes? As we saw with European options, the node is calculated by the risk neutral probability plus times the option value in case the stocks goes up, and 1 minus the probability of the option price in case the option goes down. And all this to bring into present value. Well, the only difference is that you're going to have also this variable here, which is the difference of the stock price and the exercise price at that certain node. So if this value here, let's see, is higher than the continuation value, well, the value of the option at that node, well, will be higher. And when you bring this to present value, you're gonna have something called the early exercise premium. But in case in any node, if this here is lower than the continuation value, the price will be identical. And the way to do it, well, it's basically the same thing of the European option with the one small difference. Well, all the payoffs, all the same thing. The difference is this here. Here is like all the continuation value as it was explained. And here is, for example, I'm gonna get the stock price of each node and gonna do minus the exercise price, and it cannot be lower than zero. And in case this here is higher than this value will be selected, and I'm gonna, well, get my option price based on the American option price model. And as you can see, the value is the same thing in this case, 8.76, the same thing of the European option. Why? Because the dividend yield is lower than the risk-free rate. And for call options, the dividend yield should be higher than the risk-free rate to have a difference between this. Well, so let's see what's going to happen if I change the dividend yield to 0.1. This is going to result in a difference, because when you increase the dividend yield, you're going to have an incentive to make an early exercise. And now you see is now the difference is the American price is 5.7. But let's see what is the price of the European option in this case. What was the OMAT? Yeah, you see, this is because of the early exercise. The American option is more expensive because the dividend yield is a lot higher than the risk-free rate. And in this case, it's like the opposite for put options. And well, to visualize it, I have here my calculator, and well, let's do it. Well, more or less the same parameters. I just changed the dividend yield and this interest rate to be not that large. And well, we're gonna start with 10 steps just to visualize the tree. And here you go, the tree. You can have here, instead of those ugly matrix, you can have it visual. It's possible to visualize here the stock prices at each node and the call prices. Since I'm doing an example with calls, 14, for example, here 14.3, but the ICE S minus K is 14.39, so the final value is going to be 14.39. So these yellow ones here are when there is an early exercise optimal thing here. And imagine if I have like a zero dividend yield, China no early price no notes. So that's the way to keep playing with it. But yeah, we should increase the number of nodes because like with 10 is too low, was more to visualize it. So when I recalculate with n equals to 1000, here have our insights. You see, let's see the European Black-Scholes price 3.57, the European 3 with 1000 nodes 3.57. So basically the same value as the Black-Scholes, but the American price is a lot higher. You have an early exercise premium of 0.07. And well, let's see what happens if it's like a put option. You have a very low early exercise premium because of the difference between the dividend yield and the risk rate. If I have like zero here, it increases. So yeah, that's the way to keep playing with the variables. And let's see if I increase my implied. Let's relate with the other variables like Vega. What's happening with my implied volatility? This zero. We have a 0.19, 0.20. So it affects a bit the early exercise premium thing if I change also the implied volatility. And well, this is like one of there's like a lot of ways to play with it, change the variables to see how it affects the early exercise premium. Well, so dividend yield and Q and risk-free rate are the main variables that affect exercise premium, and in the end, the difference between European and American options. Since most of traded options are Americans, and you're trading a high dividend stock, is the one you're gonna see the largest difference between the Black-Scholes model and the binomial price model, considering an add the money option. So I hope I was clear with all the concepts. And well, good luck and let's make money.